I have one more video to record as far as derivation or combining several formulas together for use in the Excel spreadsheet. And overall, on the screen, I have the derivation of displacement, change in velocity with respect to acceleration on this side. And on the other side, I have Tsiolkovsky's equation, which just relates change in velocity to the velocity of the exhaust and like actual things we would measure and try to account for when we're building a rocket, that being speed of the exhaust and the mass ratio, as NASA would call it, that being the initial and final mass of the rocket, or dry and wet mass for short. So relating the two formulas, so we can actually make a spreadsheet relating the rocket specifications to how high it will go and how long it will stay in the air. I will take the change in velocity as equation as shown here, delta V is equal to AT. I will take that and I will combine it with the Tsiolkovsky's equation. And we obtain that delta V is equal to acceleration times time, and acceleration times time is equal to the velocity, not negative, but positive velocity of the exhaust. And we are skipping several steps. Keep in mind that we are accounting for height only, or well, direction only. Assuming the rocket's going straight up, we don't have to worry about several different vectors in 3D space. And I will assume that the velocity of the exhaust is going straight down. All energy is going straight up, or all energy is being used, so the rocket will go straight up. So we obtain AT, or acceleration times time, is equal to velocity of the exhaust times the natural logarithm of initial mass, or dry and wet mass combined, over the final mass, or just the dry mass alone, after the rocket's used all its fuel. This will be useful for finding displacement. And I can show that here. We have displacement is equal to T over 2 times final velocity. I will call that final velocity plus initial velocity. And what is final velocity? Final velocity is going to be equal to V naught plus delta V, or initial velocity plus change in velocity, conceptually. This can also be written as initial velocity plus AT, as shown up here. So if I plug that into the displacement formula, then there's a way to relate displacement of the rockets to some of the rocket specifications. So we would get time over 2, and this is the point in time when the rocket starts lifting off to the time the rocket runs out of fuel. Call it point A to point B. There's several other points to worry about, but we will ignore that for now. So the displacement will be equal to, taking this, we have 2 times the initial velocity plus delta V. What is the initial velocity of a rocket that's been standing still on the launch pad? That will be equal to 0. There is 0 velocity there, right? And so we get time over 2, let me scroll down, times delta V. This will be the displacement of the rocket, and we obtain displacement. Now I will be substituting in Tsiolkovsky's equation right here. We get time over 2 times velocity of the exhaust of the rocket times the natural logarithm of the overall mass of initial over mass final. And now we have rocket specifications being related to displacement. This can be used to find time. If we know displacement, we know the velocity, like the rocket specifications. This can be used to find displacement if we know the time the rocket is in the air as it's burning fuel, at the rocket specifications, etc. Substituting, is there anything else? Let's see. AT squared plus V naught T. That should be good. We can find, we can find acceleration using using displacement and velocity. That may or may not be necessary. Say D equals AT squared plus V naught T. Using this, there is one more formula. And we said that change in velocity is equal to AT. So displacement. No, we take this formula we just derived, and we can solve for acceleration using it. So this is displacement right here, and this is displacement up above. So we get AT squared over 2 plus initial velocity times time. That's displacement. And so is the other thing. Time over 2, velocity of the exhaust. Just substitute in there. So if we're looking for acceleration, we would get acceleration is equal to T over 2V exhaust ln mass initial over mass final minus V naught T all over taking the T squared over 2 and inverting it, we get T squared. We multiply everything by 2. And this is the formula for acceleration using the rocket specifications and the time that the rocket is in the air. Remember that T is actually final time minus initial time. However, the time we start measuring the rocket's velocity, position, and acceleration will be at time 0, where time 0 is when the rocket starts actually burning up fuel. I wrote that as point A while it's on the launch pad, and it runs out of fuel at point B. There's 2 more points where the rocket reaches maximum height, and the other where the rocket hits the ground. But we call this time 0 at point A because that's what we care about. And so T will not be the change in time, but the time the rocket reaches point B, time B minus 0, or time A, which is just time to reach point B. Okay, that showing the formula, showing my spreadsheet is not working. That is fine. I will end the video there, and here we go. And we will use this spreadsheet and the formulas shown to create some equations. In bold, we have acceleration of gravity, exhaust velocity, dry and wet mass, as well as time for the rocket fuel to empty. We'll be using those 5 things to find time from points A to B, B to C, C to D, as well as displacement, velocity when the rocket hits the ground, acceleration, etc. Thank you for watching.